Hello, everybody. This is Tim Lankish from CAE Services. Thank you for joining the webinar. We are going to wait a few minutes as people continue to log in. So in just a couple minutes, we'll get started. So stand by. Okay, we will go ahead and get started. So hello, everybody. Again, my name is Tim Lankish. I am the Director of Engineering at CAE Services Corporation. We really appreciate you taking the time out of your day to attend this. This is our Ask the Moldflow Experts webinar. And the topic for today is how to identify and solve warpage problems. So why are we here today? Many of you have had to deal with a warp part like this before. You did everything right. Did things right with the gating, the cooling. Maybe you even did a DOE, a design of experiments at the press, and yet you still get this for your part. And it's one of the most frustrating parts of our jobs, right? So we're here to answer that question. How do I make a plastic part right? How can I rest assured that I can make anything no matter what plastic molding challenges is thrown my way? And for many of us in the plastics industry, that's why we're here, to make injection molded plastic parts work. It's the reason we get up every day and come to our jobs. It's what feeds our families. It's how we spend a third of our day, and a lot of that time is spent figuring out how to get our parts up to snuff, right? And heck, I've even had dreams or even nightmares about plastic parts. And if we're really honest with ourselves, we would probably admit that a lot of our solutions to these problems are guesswork, educated guesswork, but largely guesswork. So our objective is making a part to print, and getting a part to print can be very frustrating but rewarding experience. And the payoff is when your customer gives you a pat on the back because their part fits like a glove, and then they reward you with more business down the road. So here are a few takeaways that I'd like for everybody here to have when they're finished with this. So first of all, I want you to understand what part to print means, and why Moldflow should factor into that equation. And then you should understand the factors that play a role in part to print. You'll see how we use Moldflow to identify those factors. And then lastly, what can be done when all else fails, because at some point, all of us in the plastics industry get to that point. We've done everything we can, and then what? What do we do next? So I have some ideas on that. So a little bit about me. As I mentioned, I'm the Director of Engineering here at CAE. My background's in physics and math. I've been here for 27 years. I'm expert certified, and I've trained many expert certified engineers. Um, you may have seen some of my articles in trade magazines over the years, and I've also presented at the Moldflow Summit a couple of times now, called the Autodesk Advanced Manufacturing Summit. Our company, we've been around for quite a while, since 1988. We have the most expert certified Moldflow engineers in the world. More recently, in the last year and a half, we've become an Autodesk partner, and we've completed, as you can see, thousands upon thousands of jobs. So we've seen a lot of different parts from a lot of different industries, a lot of different problems. You name it, we've seen it, kind of a thing. So we've got a wealth of experience in the area of injection molding. So as I mentioned, CA Services has been around a long time, and we've worked on a lot of projects. And this is one example. You can see that part there. It's like a little mud flap on a semi. And one of the biggest lessons we've learned during that time is that it's one thing to be able to simulate and talk plastics. It's quite another to be able to identify and solve warpage problems. And that's what we've been able to do. Leverage the best plastic simulation software on the planet to be able to not only solve molding problems, but to avoid them. So let that burn into your brain. The idea is to predict the problem, identify the cause, and then solve the problem. So predict, identify, and solve. And you see the circle around that area there. That's the final product. Here's what they were dealing with initially. In the lower left, you see that little indentation in there. We were able to identify the problem there as a buckling problem. And ultimately, it was a part design issue. That area was designed to be very thin. And after trying several things, we were able to come up with a solution of thickening the wall and getting flatter parts. So in this case, you talk about money issues. Ultimately, this all comes down to money. This particular molder was at risk of losing some business here. And they had made a large investment in injection molding presses, and that could have really stung. But we were able to come in and solve the problem and fix this in rapid order. So predicting the problem with the accurate software, identifying the cause, it was a part design issue, and solving it. Thickening the part was the solution. Other ways to do this is a conformal cooling solution. You see the conventional cooling up here on the upper left. That was designed into the tool, and by using that design, there's going to be quite a bit of heat trapped here in this tight corner. By going to a more conformal cooling solution, we were able to get a 3D printed insert for that, get the cooling lines closer, tucked into that corner. You see the reduction in temperature when you look at it on the same scale, and then the result here being more uniform temperatures as measured on the press. So that change to the mold design produced less warpage. You see beforehand we were predicting some 14.6 millimeters, and afterwards 9.4. So there was still some of that warpage there. It wasn't all due to cooling, but just by eliminating that cooling factor, we were able to reduce the warpage by over 5 millimeters. So what does part to print mean? So now that we've whetted your appetite for what's possible, we want to dig into some details. We want to know that part to print is possible. We need to define what we mean by that. Most people think of it as meeting dimensional tolerances. Designers create part designs and communicate their intentions to the manufacturers in these 2D prints. And in that 2D print, they'll specify the inspection points and the corresponding dimensional tolerances. And then, they'll use GD&T symbols to help communicate everything: hole locations, surface profiles, flatness requirements, you name it. But not only are there dimensional requirements, but aesthetic ones too. And this is the one that we can see. I'm sorry. This is the one that can often cause problems with dimensions, as we'll see later. So tolerances, why are they needed? Seems pretty straightforward. For fit, you have mating parts most of the time that you're dealing with. Function, sometimes they need to be the right shape to function properly. And then aesthetics, warp parts just don't look good, as I showed with that truck part earlier. When things don't match up as far as mating parts are concerned because they're warped, you see gaps between surfaces and so forth, between edges. And this next question is a big one in the plastics industry. Who's responsible for determining those tolerances? Most of the time it's going to come from the OEM, maybe sometimes the molder, but it's the molders that are pressed to hold those tight tolerances. So they should have a voice, but also mold makers should have a voice in this too. Their reputation's on the line. When they're handed something for which very tight tolerances are required, but the part design is the problem, they can make a mold that is exact dimensions of what they need, but still have issues with warpage. So the mold makers ought to have a voice in this process as well. And then the other question that comes up is, are these tolerances reasonable? And really, it depends on who's asking the question. If you're in the fiber optics industry, microns matter. If you're in the automotive industry, maybe quarter to half a millimeter is what you're dealing with. It really just depends on the part and the industry that you're in. But Moldflow data is very helpful to that discussion. And reasonable or not, how do we achieve them? And one of the questions we often get, hey, should I jump in full force, buy software, learn it, get good at it, and use it myself, or should I outsource it? Should I rely on the experts that have done thousands and thousands of projects to be my source for using or leveraging the Moldflow data? So meeting part to print, here are the challenges. Do I know enough to avoid the problems? Can I identify the root causes of those problems? Can I solve those problems? So it really gets back to the predict, identify, solve. What don't I know? Oftentimes you don't really know what kind of problems you're going to have until you get into it. And even once those problems present themselves, it can be difficult to identify those root causes. Most of the time, your first line of defense is going to be the processing team at the press. They're going to try to dial the knobs until they get a good part, right? But if they're handed something that was doomed to fail from the beginning because of its part design, then there's oftentimes not much you can do from a processing standpoint. So what can I do to solve those problems? What do I have at my disposal? Some of the obstacles that you'll run into is, should I rely on opinions and experience, or should I rely on data? What are my unfunded expenses? If I don't know what I don't know, then how can I prepare for that with the unfunded expenses? It's amazing how much money gets spent after the fact once a problem hits the press than before the fact to predict some of these problems. And then lastly, not enough time. And the argument there really is, how much time are you spending chasing problems after the fact rather than avoiding them in the first place? And then the solution, as we are preaching here, the ultimate solution is to rely on data. You have to rely on data, reliable data, to be able to make informed decisions. It's going to reduce and eliminate those tuning loops, the after the fact after you get problems, fixing them, um, and then staying on time and within budget. So if you can rely on data as a predictive tool, then your projects will go much more smoothly. You'll avoid problems, and that's going to keep things on time and within budget. So some of the questions we get about using Moldflow data, is it really that useful? Can it help me get a flat part? How can we get the most value from our Moldflow? Will Moldflow help reduce molding costs? And how accurate is it? All valid questions. You know, if you're going to invest in either buying the software or using Moldflow services, then these are questions that need to be answered. And we'll talk about that here as we go through the webinar. So let's get the first one, maybe one of the most important ones out of the way. How accurate really is it? This is something we worked on 10 years ago. Here's a critical dimension that needed to be met, and the predictive analysis on this showed that we were about 1.7% off, so pretty darn accurate. And more recently, we worked on a project. This was actually a part for a ventilator from the COVID crisis. We had some molded samples. We ran this through Moldflow with good material data, and you can see how much that blue part there warped upwards relative to the expected shape of the part, the flat shape. And then when we scanned the data and compared it to the Moldflow predictions, we were within, 54 microns essentially of the predicted. Very good. So this is more recent stuff. So when you have everything right in terms of your data, Moldflow can be very accurate. I am not going to stand here and say that Moldflow is 100% accurate in every case. It's not, and no one should expect that. It continues to get more and more accurate as years go on, and the R&D efforts of the Moldflow team continue to improve where in areas where things are lacking. So there are certain types of parts, there are certain types of materials for which things tend to be a little less accurate. But we will talk about all of the things that go into getting the most accurate results out of Moldflow. One of those things is defining your objectives. And that's really the key to success on any project. These objectives can range from, knowing what your tolerances are to, where can I put my gates? Is this going to be an appearance part? Are we allowed to change the part designs? These are the discussions that have to happen rather before you start any project when you get into Moldflow. Otherwise, there's a very good chance I can get you a very flat part with very little aesthetic issues, but it can't be molded because I'm not allowed to put a gate there. Or putting a gate there means I'm going to have more warpage than I expected, but it's where the knit lines are best. All of these things can kind of play against each other, as we'll see. So you have to prioritize those objectives. And as we know, anybody that's spent any time in the plastics industry, is that plastics manufacturing is not perfect. There can be a lot of slop and there can be a lot of black art to it. It's really a balancing act. And what I mean by that is that when you emphasize one objective, it can often impact the others. For example, if you are focused on aesthetics, such as, you can't have gate vestiges in certain areas, or you can't have knit lines in other areas, that's going to impact your tolerances because the filling pattern matters to how much a part is going to shrink, how much shrinkage variation there's going to be, and therefore how much it's going to warp. So those tolerances or the quality issues are going to impact time. So the tighter the tolerance, generally speaking, the more time you're going to have to spend on figuring out how to get the warpage reduced, for example. And then the more time you spend, typically that's going to impact your cost. Engineering time and oftentimes the solutions themselves tend to be a little bit more costly. So it's important to know, not only know what your objectives are, but to prioritize them. Which ones are the most important to you. So you try to knock the top ones off and do the balancing act the best you can, but with the understanding that oftentimes there's going to be trade-offs. So part to print depends on all of these factors. The first one of which we're going to focus on, rather, is the mold design. And this really boils down to two things that I think are most important. First of all, gating. And I would argue that this, in most cases, has the greatest mold design impact. It's often driven by aesthetics. For example, in this case, we have a door panel with a map pocket there, and we're not allowed to have any visible gate vestiges, and we're not allowed to have knit lines in the map pocket. So to my point earlier, if I'm a Moldflow analyst and I'm not told this, I could guess at some things, but generally speaking, I'm going to go throw gate locations on there that give me the biggest process window. And what I mean by that is, maybe reduce the pressure by balancing out the flow. Reduce pressure means reduce clamp force typically, and reduce clamp force means I can run it in a smaller injection molding machine and reduce my molding costs. So not a bad idea, but you'd hate to get to the point where you manufactured this mold and got to the press and saw, well, I've got these knit lines in the map pocket, that these parts are no good. So knowing what you have to do for gating to avoid that matters to what we're going to do in the Moldflow analysis. So this is the final solution we came up with on this one. This ended up being a 9-drop scenario, and we valve gate sequenced to let the flow get through the map pocket, and then gradually boosted the flow in sequences there. Also, knit lines can be important to the structure of the part. There's reduced mechanical properties at the knit lines that can cause a part to fail if you're not paying attention to where those knit lines end up. If they end up in areas with high stress, mechanical stress concentration, then you can get yourself in a lot of trouble with that as well. So I just want to illustrate this with an example here. So here's a part. This is a long glass fiber reinforced material. This is a common gating scenario for this type of part that had been used on previous generation tools for this type of part. And you can see large knit line in the middle, large knit line between all the gates really. Here's a 2-gate scenario, gating at the top, getting all the flow in one direction, but still a knit line in between gates here. Here's one with 2 gates on the bottom side, and here's 3 gates on the right side. So all different options to see which one turned out the best. And obviously you can't test this out in real molds, or it would be a very expensive test. As I mentioned, this is a long glass fiber filled material, and we have the ability in Moldflow to predict the fiber orientation pattern. So for all these different scenarios, the 3-gate, the 2-gate on top, 2 gates on bottom, and the 3 gates on the side, you can see how the fiber orientation plays out. And that fiber orientation matters to the shrinkage. On the top example here, we have an unfilled material, and you see the flow direction there. The shrinkage in the flow direction tends to be larger than that cross flow. But when we go to a fiber-filled material, the shrinkage in the fiber direction tends to be less than that of the cross fiber, and the magnitude of difference, the ratio of the difference of the shrinkages in the different directions tends to be much larger. Sometimes 10, 11, 12 to 1 difference in the shrinkage. So one of the things we try to do is get all those fibers going in the same direction to help mitigate those shrinkage variations. So here's a prediction of the warpage due to fiber orientation effects, those shrinkage effects for each of those cases. So in this case, the amount of warpage was predicted to be 13.1 millimeters, 17.7 when we gated on the top, 11.9 when we gated on the bottom, and then finally 6.9 millimeters of warp when we gated on the side. We were not allowed to direct gate this. So you can see we kind of covered all of our bases in terms of all the different ways to gate this, and still ended up with almost 7 millimeters of warpage, right? So it's really important to understand that there are many cases where you can reduce warpage and still get a fair amount of warpage. And then we'll talk a little bit later about what do we do then. But as we're doing this, you'll see in the next slide here that the gate locations affect the pressure and tonnage. So what's best for processing, as I mentioned with that knit line example earlier, what's best for processing isn't necessarily best for the part. So in this case, this isn't the most egregious example, but it illustrates what I'm getting at here. With the 3 gates, 3,700 PSI and 835 tons to process this out. This option over here, we see a little bit more pressure, a little bit less tonnage. Here we have 4,400 PSI and about the same tonnage when we gate from the top. But the scenario that was best for warpage produced the highest pressure because we have a much longer flow length across the part, and the highest amount of tonnage because we have that higher pressure scenario. So this is still very much within the processing range. It's not difficult to process, but there are going to be those times when you get into a situation with, say, a very thin-walled part and maybe a polycarbonate material that tends to drive your pressures up. And in those cases, you have to really pay attention to where you are with those process settings when you're able to reduce the warpage. So keep that in mind as you go through projects like that. So that's gating. That's the first side of the mold design equation. Cooling obviously plays a very big role in warpage as well. So unfortunately, that's often the first area people look to try to solve warpage problems, but it's not necessarily always the best, but it does come into play very often. In this case, we have a small reflector piece. We have a hot core with conventional cooling. They have a couple of thermal pins in there. But you see there's some heat buildup inside that deep core there. So the solution we came up with on that was to introduce MoldMax cores to the equation and make sure that we had cooling inside those MoldMax inserts. And you can see we're on the same scale here, and we're able to get the red out, so to speak, with efficient cooling from the MoldMax. We also introduced a couple of baffles into there. So by doing so, we were able to reduce that temperature some, 25, 30 degrees in that area. What that does is reduces the temperature differential between the core and cavity and reduces the thermal bending in those walls. And you can see without the MoldMax, these two walls were caving in some 0.86 millimeters. And with the MoldMax rather, we reduced the warpage by about 1/4 millimeter. Doesn't sound like much, but when you have optical parts, things like that, every 1/10 of a millimeter can matter. So, so that was one solution to help reduce the warpage, right? So, and again, and this is a lot like the gating situation where it may not, so a lot of these solutions may not get you all the way there. So what do you do next? And again, we'll talk about that later. Another contributing factor to part to print is the part design. You know, I talked a lot earlier about, you know, molders are responsible for the outcome, but oftentimes they don't have much say in the part design. They're handed a part and expected to make everything work just perfectly, right? So we'll talk here about how part design matters to the warpage of a part. And it boils really down to being a shrinkage related issue. On the left is just kind of a graphic to show you what happens in a part. You know, you have a gate on the left-hand side, areas closest to the gate see higher pressure, and when you see higher pressure, you see lower shrinkage. Conversely, on the end to fill areas, you see lower pressure and therefore higher shrinkage. So I mocked up just a little design over on the right, and just to illustrate this, and you can see up in this area in the upper left here, we have a thicker part. In the lower right, we have a thinner wall, and we also have a rib that's even thinner than the wall it's attached to. So I just gated this right in the center just to, you know, essentially gives equal flow distance to both sides of the part here. And you can see how much more, I exaggerated this for effect, but you can see how much more the thicker area shrank laterally than the thinner area. Also notice that the even thinner rib is bending the part down. It wants to hold its length because it shrinks less than the area that it's, or than the wall that it's attached to. So it's trying to bend that part down to maintain its length. So you can use this information to your advantage to help you design a part that A, reduces the shrinkage variation among the different areas of the parts, and B, helps you design ribbing structures that can either induce warpage to counteract, you know, opposite warpage, or B, you know, eliminate ribs to counteract warpage that the ribs are causing. So, and that's where you know, Moldflow really comes into play. You got to know where to put the ribs. You got to know how to design things to take advantage of these situations. And you know, Part Design 101 says let's keep the wall thickness variation to a minimum, right? And this is why, because they shrink at different rates. And when they shrink at different rates, they kind of tug at each other and cause warpage in the part. So here's an example that we worked on. Here's the original part design. You see the gear teeth are straight, and they struggled a little bit with this part with the warpage, because when it warps inward, as it's showing here, again, this is exaggerated by a factor of 10, but shows how this part warped, and they got very good correlation with the Moldflow results on this. It was causing some issues with the mating of the gear teeth here with its mating part. And they were moving to a new generation tool that was going to have helical shaped gear teeth. So they wanted to improve on the warpage on that new generation tool. And this is really why I love Moldflow so much, because it allows us to separate out the different causes of warpage and how much each cause is contributing to the overall warpage. So pay attention to the numbers on the screen there. They're a little bit small, but you should be able to see them. The cooling factor. So what these plots are showing is the radial deflection, the radial component of warpage. So anything positive is out from center, anything negative is in towards the center. So, you know, we're talking less than 1/10 of a millimeter for the cooling and orientation effects. I should say less than 1/4 millimeter. So very small contribution. But look in the upper right, the shrinkage component of that, we're seeing negative 1.4 millimeters. So you look at that and you compare it to the total warpage in the lower right there, and you see a pretty good match. So this tells me immediately that this is a shrinkage issue. And by shrinkage, I mean, you know, shrinkage due to packing, gate location, wall thickness, etc. So this was a fiber-filled material, and lo and behold, the fiber orientation didn't really make that much of a difference here. I'd say the lion's share of the projects I work on that have fiber-filled materials, it is the fiber orientation that causes the warpage. But in this case, it was a bulk shrinkage issue. So that told me where to go focus my efforts. And one of the things I like to do is on any project I work on, I don't want to rely on processing to have to fix my parts. If you have to rely on processing, oftentimes that's telling you something. You've got a very tight molding window, and it's harder to hit that bullseye. So we want to try to hardwire things into either the part design or the mold design, preferably the part design. Hardwire solutions into it, that is. So that's where we looked. We went to the part design itself and played with different options to see what we could do to reduce the amount of warpage here. So here's one option with some large ribs. You can see there's a pretty good reduction in warpage, but these large ribs were going to cause some issues with some mating parts. So we drilled down to a few other options. This was an option presented by the OEM in this case, which would have caused some tooling issues. Same here, pretty good amount of warpage, and they actually wanted the warpage to bow outwards rather than inwards if it was going to bow in any direction. So the magnitudes here were very good, but again, a little bit more difficult to tool. So the final design that we landed on was this design, much easier to tool. We essentially cored material out of that thicker wall and those sidewalls there, and we're able to produce that outward bow and reduce the magnitude by quite a bit. So you see the power of playing what if here, and again hardwiring it into the part design to get the effects you want. And so in this case, this particular part design will work over a wider range of process settings than the original one did. So that's part design. Next focus is on material. Now, most of the time, you're not going to be able to change your material. It is what it is. But I want to emphasize how important material properties are to Moldflow prediction. So my statement here really rings true, and I've run many examples where substituting material can get you in a lot of trouble. It can give you bad results. It's all about garbage in, garbage out when you're doing simulation work. So here we have exact same gating and so forth, exact same process settings in both of these situations, and you can see the filling pattern on those. But look at the pressure differences. We have a valve gate sequence, and each of these peaks tops out at just over 10,000 psi. You look at that and you say, oh, I can do that in my injection molding machine. I can do anything up to 25,000 psi, no problem. Well, they got that to the press, and they saw quite a surprise here. They couldn't mold the part, and the reason was something called juncture loss data. And there's many materials in the Moldflow database that don't have this juncture loss data. So without the juncture loss data, you can see well under predicted. So imagine their surprise when they got to the press and couldn't mold it. So it's really important to have the right material data when you're running any kind of Moldflow analysis. So when you predict pressures improperly, the amount of packing pressure that you are applying to the model doesn't make it to the part like it should. So your shrinkage predictions are off, and therefore your warpage predictions are off. So there's a lot of things that go into these predictions, and to the extent that there's uncertainty in any one of them, is going to snowball down to the warpage results. There's something called CRIMS data that also affects warpage predictions, and certain types of models that we run in Moldflow. Here's a case where, with the CRIMS data, it predicts some 6 millimeters of warp. Without the CRIMS data, the total warp was 3 millimeters. So initially, and this was a real mold, where they insisted that we run the Moldflow despite our objections saying there was no CRIMS data available. So we predicted 3 millimeters. They went with it. They ended up having to scrap the cavity side of the tool and build a new manifold, a year later, because by then the material had been tested properly, and we ran it, and sure enough, we predicted exactly what they were getting. To solve that problem, we were able to run some different gating scenarios to get better results. So this CRIMS data is very important. Shrinkage data in general is very important. This was another part that we worked on. I did a full webinar on this at the Advanced Manufacturing Summit for Autodesk back in August. So look to their website if you want the whole story on this. But when we initially ran this, we were showing the right direction of warpage, but the magnitudes were too high. So we looked back to the material data. The material was retested, and we got much better predictions that we could use to then go into a windage solution, to apply windage and get flat parts, all done in very rapid order within a week. So it's incumbent upon the Moldflow analyst to know when to call BS on parts that they think are out of line with reality. And it takes a lot of experience to know when to do that. So, but the overall message here is that the material properties matter. The juncture loss data, the CRIMS data, shrinkage data, mechanical properties, thermal properties, PVT properties. There's a whole lot that goes into this, and again, uncertainty in any one of those can propagate throughout the process to give you wrong results. So that was material. Now we're on to process. And again, message I want to get across to you is that if you have to rely on process to fix your parts, then you probably ought to look back to your mold design or part design to see if you can improve on that. But let's just show a couple of examples on how process matters. So here's an example, a medical part where there's an air trap in this little, I think it's called a cannula. Very thin wall there next to other walls that are thick. So we see the path of least resistance effect coming into play here. Areas that are thick are going to fill a lot easier than areas that are thin. So you see this hesitation causing a backfilling condition there, and that can either cause a void or a knit line or non-fill, what have you, in those areas. And in this case, it can cause some structural issues, compromising that area that's likely to see a load. So that was when they filled it at 1.1 second. If they had the ability to fill this faster, that can cause venting issues, what have you. But filling faster is one solution to this, just by changing the process. But again, when you have to rely on that, sometimes you're not going to be able to achieve the process that you need to fix the problem. In this case, the real solution was a part design solution by thickening this area up and reducing that hesitation effect altogether over a wide range of fill times. Packing pressure and time. This is a big one, and this is a two-shot overmold. I got some questions beforehand about whether or not we can predict warpage with two-shot overmold, and the short answer to that is yes. And in this case, I see this a lot with processing standards at different companies. You have your book of standards, right? And a lot of processing teams say we will pack at this amount of time for this material no matter what, and that's a bad way to go. This is one of those cases where I don't remember the exact time off the top of my head, but it was a very short packing time, something like 5 seconds. And when you do that, you're you're affecting the shrinkage of the part in question. So in this case, you see a very large amount of warpage in the part when you pack a short time. And then when you pack a much longer time, you see how much the warpage changed. I mean, we're talking 41 millimeters here versus like, 5.8. So it seems so intuitive, but yet these are practices that are a lot more common than you think out there. So there's the differences. So that's processing. Again, the point to take home there is don't let it get to the point where process is your only solution. And then lastly, to get a part to print, at least this is how we feel. I mean, we've done this for many, many years, but it really comes to bear. Simulation expertise really matters in this. There's an awful lot of poor simulation being done out there because the analysts aren't well trained and don't realize how much each of those input variables matters to the final result. It helps us know when results are reasonable and when they aren't. We talked about material data. You'll see an example about mesh here in a minute. It's not just knowing when the results are reasonable, but knowing how to fix things. We talked about predict, identify, solve. Okay, it's one thing to predict things, but it's quite another to know what to do with that information. You got to know how moving gates or improving cooling is going to affect the results. You got to know how to process things to fix aesthetics or warpage. You got to know how to change part design to fix warpage, and you got to know how to use windage to fix warpage. Here's an example of how poor mesh got one of our clients in trouble. They put 1 million elements on the simulation model in this example, and no knit line predicted. See the big knit line that showed through the chroming, pretty nasty looking there. So, and then just looking at this with a much tighter mesh could have avoided that problem. So we were able to predict that knit line right where it occurred, and then offer some solutions to fix it. But one thing to note is that when you get into the situation, now you're a little bit handcuffed. There's only so much you can do once the tool's built to fix problems. You have a much wider range of solutions when the mold's not yet built, and you can change things to put into your design, whether it's the part design or the mold design. So I've been talking about, what happens when all else fails. Maybe you did everything you could with gating and you still got that fiber orientation pattern was great and you still got that large amount of warpage, or you put mold max into your cooling design and you still got some warpage. What do you do when all else fails? So you guys are probably sick of seeing this curve. This is the old coronavirus flatten the curve graphic that we saw back in March and April of this year. But that's kind of what we have to do. We got to flatten the curve, and we do that by using windage. Okay, so if you haven't heard of windage before, it's all about modifying the tool to be able to have the part warp back to flat. So you're essentially manufacturing the mold in a shape that is different than the design of the part. So you can do this when tolerances are reasonable. Simulation inputs are solid, and we've talked about how important that is. When all other options have been exhausted, and you can't change the material, you've looked at all the gating and cooling options, you can't process it out, and the part design modifications haven't worked. So these are conditions under which using windage is a good idea. So here's an example of that. Here's a filling pattern that produced this fiber orientation. We played around with different gating options, and one of the things you want to do is get as much warpage out of there as you can. In this particular case, they're used to putting 3 gates on that larger piece there in the lower right. We did that, but it actually produced more warpage than single gate option. But even with the single gate option, you know, we were seeing too much inward warpage on those where those 4 arrows are, and then too much upward warpage where that arrow on the lower right is. So here's what windage looks like in simulation world. So here's the nominal or intended position of the part. And these are going to be our guidelines, the red lines there. So what we do is we start the position of the part biased outward. So this is what it's going to look like in the tool steel, as opposed to what it would have looked like in tool steel had we not done windage. It would have been in this position. So we iterate on that. We can change the windage factor, as we'll call it, to the point where it warps back to the position we want it to the target, warps back to nominal. So that's great. You know, in simulation world, we're able to, you know, in this case, even remove as much as 15 millimeters of twist. Looks great in simulation, right? But the real trick is in the CAD morphing, because there's some corrections that have to be done to make it toolable. And one of those corrections is die draw. You know, you twist the part and you see a part with this many ribs on it. It's bound to happen that a lot of these features are going to go out of die draw and put you in a die lock condition. So the real trick is being able to morph the CAD to the point where you have a moldable condition, but also a shape that gets you back to the nominal part through windage. So you can see here in purple, we have the windage condition, and all those ribs, although it's difficult to see from this angle, are in die draw so that there is no die lock. What's the cost savings of this? You know, traditionally, here's what you would see happen without using simulation. And pay attention to that center column there. This is what happens after the first tryout. So we're already late in the game here, and everybody's expecting things to happen. You know, they're putting pressure on you to get parts and so forth. You know, if you add everything up and let's say you got 4 tuning loops and 9 to 13 weeks after tryout to get this all worked out, because you had to try it, you know, try it one time, correct it, you know, all the shipping back and forth, times at tryouts, you name it, that all adds up. And this is a typical cost for these oil pans, by the way. That's not uncommon through traditional methods. But when we use Moldflow windage analysis, now look at the center. So this is happening before tooling even starts, is even kicked off. You know, we can do the analysis within a week. We're talking 2 to 5 days for, you know, doing the windage study and the CAD morphing. Sometimes there may be a tuning loop afterwards. For example, in this part here, some of these side bosses had to undergo a slight adjustment, but that's a heck of a lot better than, you know, 4, 5, sometimes up to 10 tuning loops. So you see the improvement in time, and this time is being absorbed prior to mold kickoff. So, and there's a substantial cost savings on that. We have to manage expectations. This is important not just for windage, but for all analysis. You got to think of the unfunded expenses that are required to resolve a problem. You know, how many times have you gone through a project where, you know, you had to open the checkbook, so to speak, after the fact and solve that problem? You know, another expectation is that Moldflow is 100% accurate on everything. And as I said before, that's never ever going to be the case. It's going to improve and improve and improve and improve, but it will never be 100% accurate. It should be very accurate. And I showed a couple of examples where that was the case. And again, it's incumbent upon the analyst to know when to believe the results and when not to believe the results. But in any case, it's way more cost effective than trial and error methods. There's really no better way to achieve part to print than through using Moldflow correctly. And correctly is the operative word there. So some takeaways here. So leveraging Moldflow helps you achieve part to print. It helps you use data to inform your decisions. You know, it eliminates that guesswork. You know, we all have a lot of experience in fixing problems with injection molded parts, but nothing is more useful than having data. Leveraging Moldflow also helps to identify the best way to achieve those goals. I showed how Moldflow is able to separate out those different contributing factors to warpage. So it helps us focus on the right area to fix that problem. And by doing so, that really helps you manage your timeline. You know, if you know where to focus your efforts, you're not going to go down a lot of wrong paths to fix the problem. And that's unfortunately how it's done, you know, traditionally in the injection molding world. You build the mold, you run some parts and see what's wrong, and then go fix them. You know, maybe you guess at cooling, maybe you guess at processing, maybe you guess at you know, gate sizing or something like that. Whatever it may be, people have their own approaches, but oftentimes, you know, they're going to guess wrong. So being able to identify those things that cause the problem are going to help you manage that timeline. It's also going to help you manage the budget because you're not wasting that time and you're not wasting resources solving a problem that can't be fixed by the methods that you're choosing. So, like I said before, making a part to print can be a very frustrating but rewarding experience, and the payoff is when your customer gives you a pat on the back because their parts fit like a glove. So that's the main message I want you to come away with today is leveraging Moldflow to help you solve molding problems does a lot towards getting your parts right and improving your relationships with your customer. So what's new here at CAE? I mentioned the Autodesk partnership earlier. We sell the Moldflow software. We are tasked with training and mentoring as well, and that's really where it's all at. I mentioned time and again how important it is for people to run Moldflow right, and without that training and mentoring, I would argue that a lot can go wrong. On the learning side, we're all about building expert analysts. We have classroom and online training. We have Ask the Experts webinars like this one on a bi-monthly basis. We have Moldflow office hours where if you just want to sign up for some time and talk Moldflow, whatever the topic may be, feel free to do that. And you can always look on our website or follow us on LinkedIn. So with that, I am going to answer a few questions. Bear with me a second. So first question I have is from a correlation of warp, what do you consider acceptable level of discrepancy between the analysis and actual molded article? I get this question all the time, and I talked about accuracy. It's got to be very accurate, right? And you saw a couple of examples where it was very accurate. But what is acceptable? Give you an example here. So let's say I run a Moldflow and I get a warpage prediction of 5 millimeters. And I'm 20% off. So that's plus or minus a millimeter, right? But I've predicted the right direction of warp, and I'm able to look at different scenarios, cooling, gating, what have you, that tell me which scenario is going to give me the right result or give me the best solution, so to speak. So 20% is a number that I've worked with. You know, more often than not, I'm within 10%, and very often I'm within 5%. So ultimately, it's a personal decision for your company as to what's acceptable. But by and large, most of our results done properly are going to be within that 10% range. Okay, and there again, there are situations where you know, you're going to get much more uncertainty in that, and it's just the level of experience knowing when those situations are likely to occur. Next question. How is Moldflow changed by something like Mucel gas injection? So for those of you who don't know what Mucel is essentially there's a supercritical fluid like nitrogen or carbon dioxide that is mixed in with the melt. And by supercritical, what happens is the material, the nitrogen or the carbon dioxide is essentially dissolved into the melt. And when it gets into the cavity, microbubbles are created. And the idea there is to reduce the weight to thickness ratio, and it also helps improve the warpage by essentially allowing the bubbles to do the packing of the part. So Moldflow has the ability to predict such things. In fact, I gave a paper on that at the Moldflow Summit, you know, some 7 or 8 years ago. So yeah, so things have to be accounted for to look at Mucel and Moldflow. Next question, does runner and gate size contribute to warpage? Absolutely. Runner and gate size determine pressures to fill the part. It also determines shear rates as materials passing through the gate. Shear rate determines viscosity, and all of these things, you know, are interplaying with each other. And to the extent that those determine the pressure in the part, pressure leads to shrinkage predictions lead to warpage predictions. So absolutely, those things are big contributors to warpage. So we have to pay attention to runner and gate sizing. Another question that's a little bit more deep into the woods, but I'll address it anyway because several people asked it. If 3D and dual domain models give different warped shapes in the part for Moldflow, which model can be trusted? So this is for you Moldflow users out there. Again, I talked about how much experience matters with interpreting Moldflow results. There are different types of mesh that can be used, different types of simulation models you can use, and oftentimes, you know, we run those different models, you know, 3 different types of models for the same part as kind of a check. And when they all agree, then we have a lot more confidence in those results. But typically, you know, depending on what type of material properties are available for the different types of mesh, the CRIMS data for dual domain and midplane, and mechanical properties for 3D. Generally speaking, I guess what I've seen over the years is that midplane and dual domain tend to be a little more accurate than the 3D, but 3D technology is evolving, and you know, it's continuing to get more and more accurate. So eventually 3D is going to catch up with dual domain and midplane. But that's the beauty of knowing what you're looking at, you know, the experience of running a lot of different simulations and knowing which ones are more accurate in which situations. Can we predict warpage on 2-shot parts after molding and after passing through ovens for annealing or paint cure? So I showed an example of 2-shot molding where we predicted it. This is another common question I get. So yes, we can predict that. The second part of that question is, can we predict what's going to happen after annealing or paint cure? The answer is no, not in Moldflow directly, but there are links from Moldflow to other simulation packages like Abacus or ANSYS or what have you, where you can pass on the residual stresses from the manufacturing process as inputs for the annealing process simulation in those other programs. So can't do it directly, but it can be passed on to other programs that can. Many a time we do not have the actual material used in the Moldflow library. How do you tackle this issue? Short answer to that is very carefully. I talked time and time again about how important those material properties are to the results in Moldflow. So, you know, you can't just compare materials based on material sheet data. And you know, this could be a topic for a whole webinar right here. But suffice it to say, don't just rely on like Moldflow index and you know, maybe shrinkage numbers from a material data sheet to cross-reference things. It's really a lot more in depth than that. I mentioned, you know, the PVT properties, the thermal properties, you know, at various temperatures, the CRIMS data. All these things are very important to understanding what happens in a Moldflow analysis. Next one is there a follow-up on windage in regards to what was put into the tool to counteract warp to see if it was a correct prediction? So, I mean, follow-up, obviously, whenever we do windage analysis or any type of analysis, we want to get feedback. But, you know, that's part of the windage process in simulation is you have to run various shapes in Moldflow to see which one gets you back to the flat result. The temptation is to say, well, if I've got a millimeter of warp, well, let's just bias it a millimeter in the opposite direction. It's not that simple. You now have a new shape and it may not come back a full millimeter. And I also mentioned all the die draw issues. Die lock is a big concern, obviously, when you have ribs that go out of die draw. They have to be accounted for, and that changes the shape one more time. So you have to be checking all of your windage results in Moldflow first before you check the box that we're good to go, so to speak. Okay, I think that about covers it. So I just wanted to say thank you for taking the time out of your day, like I said, and feel free to email me or visit our website for any more information you may have. I'm sorry I didn't get to all the questions. I know there are a lot of them out there, but time is of the essence here. So if you have any other questions, give me a shout. I'd be happy to answer them. And thanks again for attending. Have a great day, everybody.